not. I'm gonna keep going. Geomatica BAMF is our latest release. So you know, we've talked about the what's in the new release in previous webinar, but today what we're going to talk about is Sentinel-1 TOPS. So we're going to go through the Sentinel-1 TOPS processing workflow within Geomatica. We're going to talk about interferometric processing walkthrough and give a bit of a live demonstration, show you some galleries, give you a sense of best practices for processing TOPS using, we're going to recommend that you use some of the scripts that we've developed, some Python scripts that is what we think is the best way to achieve the most consistent results. Then we're going to turn our attention over to our SAR experts and have a quick little chat. Then we're going to show you a couple of case studies, and some of the SAR experts might stick around and help us add some color and explain what we're seeing. They're more than welcome to do so. Got two case studies. One is on a earthquake situation over Ridgecrest, California, and the other one is a temporal deformation analysis over Belridge in California. So just an overview of Sentinel-1 A and B TOPS processing. So basically, a lot of the advantages around Sentinel-1A is that it covers the world very consistently. So it's on a fixed orbit, fixed collection capability, and essentially you're getting an image every 6 days. I've got a slide coming up that shows you what the revisit is over Belridge between Sentinel-1A and 1B, and there's basically an image available every 6 days typically. It has wide area coverage. The full typical mode for interferometry is called interferometric wide, or IW. A lot of data is collected in this mode, and it provides a lot of coverage on the ground. So we can get a lot of data. The data, of course, is free and open. There's an API for downloading the data. And if you don't want to use API, you can go to the ESA Sci-Hub website and download images that way. So the TOPS data format. So PCI basically implemented support for Sentinel-1 a few years ago. The first Sentinel satellite was launched in 2015, in late 2015. And we added support for the ground range detected data pretty soon after that launch. However, we had not quite added the support for TOPS data until this release. And I'll go through a few slides that give you the context or explain to you some of the challenges with processing this data, but basically it has to do with the way that the data is collected and how to assemble that. What we wanted to do is to basically make it easy for end users to work with Sentinel-1 data as a complete image as opposed to having to work with subsets. So these are the characteristics. This is kind of an illustration from the European Space Agency that shows the antenna swinging pattern, basically, where the illumination happens across multiple swaths, and it also happens across multiple bursts. So if you're trying to make a single image out of all of these sources of all of these measurements, all these backscattered measurements, basically there's a lot of work that goes into that, and you'll hear from our SAR experts later on some of the challenges, but hopefully also kind of what they were thinking in terms of making it easy for you, the end user, to work with this data as compared to some of the other ways that the data is handled in other software. This is kind of what it looks like. So if you're doing interferometry, basically what you want to do is you want to have two images that are perfectly aligned and that they're assembled the same way, and that each pixel is basically a physical measurement of the ground. And so if we're trying to leverage the phase information from those images, so assembling two images from Sentinel-1 TOPS data into a single image so that you can achieve that is a little bit more involved than what we have done because of this this acquisition mode, this TOPS mode or TOPS methodology for collecting the wide swath data. You can see here a reference in a dependent file. This is just an illustration. It's not showing all three swaths, but you can see that the swath locations are different and the burst locations are different from image to image. So it's not a matter of simply stacking those one on top of the other. You have to assemble them correctly so that you can then perform the stacking one on top of the other. So this is just showing you how they're organized spatially, and you can see that image 1 on the left and image 2 on the right has different amounts of overlap between the swaths and the bursts, and So what we've been sort of busy doing is making sure that this is completely invisible to you, the end user. We do all of the heavy lifting when it comes to organizing the data so that you can work with it more seamlessly. This is what the data looks like in raw form. So you can see that there's 3 individual swaths, and there's a number of individual bursts along each swath. And if you're working in Snap, then it means that you have to identify one of the swaths where your area of interest is located, and then you have to deramp the data and perform your processing and sort of work that way. Our kind of philosophy was to assemble all of that for you into a single image. So here what you see is basically that same image that's been assembled into one contiguous image. So it's a lot easier to work with. You can process the entire image all at once, or you can subset a piece of it and work on a particular area. So as I said, the debursting gives you, the user, a contiguous geocoded image, which is easier to work with, we think. We eliminate the redundant overlapping areas from the images. So that gives you an easier way to interpret. And it removes the need for you to identify the location of your area within the different bursts and the swath and so on. So we want you, the user, to treat this data just like any other radar data. So you can run our ingest algorithms on the data. We do all the heavy lifting, and we give you a complete image or a part of an image all the way through the processing chain. So I'm gonna just quickly move over to a Python script at this point. So I'm gonna share with you some of the scripts that we have. Now, these are some of the scripts that I've written, and Jason is helping with some of them. We have other scripts available that Gabrielle has written, and they typically go through our support team to make sure that they're well documented, and then where they usually end up is on our support website. So if you go to support.pcigeomatics.com, you'll find under InSAR some Python scripts that are available. We did post some previously for doing InSAR for RadarSat-2 data and other data sets in the past. So if I just move over to my Sentinel-1 folder here, I have one of the data sets that I'm going to be featuring later, which is 2 images collected over the same location. So these are Sentinel-1 Interferometric wide images. You can see that they're quite large. Whoops. So they're about 7 gigabytes each. And basically what I've done in this case is I've written myself a little script that leverages the Python API and the algorithms that were developed by our team to ingest the data and then to perform all the different steps. So we have the raw image, the dependent image, the external DM, and the location of the output folder. And then we just systematically go through, ingest the radar image. Here you can see that we're specifying a specific window that we want to process. In this case, it's the window which was the epicenter of the earthquake over Ridgecrest. And then we do the co-registration of the radar data. And then after that, we can generate the interferograms and perform all of the other steps. So I'm not going to give you a full live demo, but I did want to give you a sense of how that works. And before I go to the discussion with our SAR friends, I'm just going to go up here and make sure I cover this one. Right. So what I didn't do previously, sorry about that, is I didn't explain the workflow. So basically, if you've attended our previous InSAR webinars, you'll be familiar with this. It hasn't changed. Everything is the same. And that's really something we want to emphasize, is despite the fact that we're talking about Sentinel-1 tops, all of this is exactly the same as any other sensor. So basically, you take the SLC data from the vendor, in this case ESA, perform the SAR ingest, do the co-registration, generate the raw interferograms, remove topographic effects and atmospheric effects, and then filter, and then you can unwrap the interferograms. And in this case for Sentinel-1, primarily what people are interested in doing is using it as a way to measure deformation. So we've got an example over Belridge that we're going to be showing later. But at this point, I want to introduce, I guess, I'm going to bring over, why don't I bring over Gabrielle and Guy, and maybe John, you can scooch in as well. We're going to turn on the mic. for those guys? Okay. So just a quick few words of introduction. So basically who we have here, I don't know if they're sitting in the same order as the slide, but
Nope.
we've got Guy, who is our senior SAR software developer.
Nope.
We've got Gabrielle, who's our senior SAR scientist, and John, who's our senior SAR scientist, or most senior SAR scientist. So how you doing, guys?
Good.
Great.
This is on right now, right?
It is on. It should be working. So I'm not sure who wants to take the question, but I've already alluded to it a little bit, but maybe you guys can give us a sense as to what was the design philosophy behind the tool that was built for Sentinel-1 tops?
I mean, as much as possible, we wanted to make it exactly the same as using any other sensor beforehand, or that came before it. So as you were explaining, the tops data comes all bursted into different swaths, and handling that piece by burst by burst or swath by swath is more hassle than we felt was really worth for the user. So we wanted to do that hassle for them, so that as a user, you don't have to worry about bursts or swaths or anything like that. If you have an area of interest, you just draw it out, and we take out all the necessary information, process it, and handle all that for the user under the covers, so that it's basically as smooth as can be.
So I can imagine there's a lot of metadata that needs to kind of move along the way. Is that sort of part of the challenge, was to making sure that all of the information that's used for interferometric processing is sort of moved back and forth and so on?
Yeah, in terms of that management, the hardest part was getting that extra overlap information that you mentioned that we discarded, but really we tuck it away somewhere else in the file. We do need it later on for the proper processing in the InSAR workflow, and making sure that that's where it needs to be, that has the proper metadata. If you take out a subset or your area of interest, make sure that the necessary information comes along with it. It was many things to keep track of.
Great. Maybe John or Gabriel, one of you can tell us why you think this is unique. Like what makes this unique? What are users going to like about it?
Well, from our perspective, we're trying to address most of the operational users. And so tops data, for instance, even the burst mode, or sorry, the order of the bursts and the swath orders and things, unless you're a knowledgeable user, you don't even know which is burst 1 and which is burst 10 sort of thing. So we basically oriented the whole image into one complete segment, and then allowed you to process that. So you don't need to know the burst numbers, you don't need to know swath numbers. You already sort of alluded to that. I think the other important thing too is, as far as I know, we're the only people that handle it as a single channel, so it's all complex valued. So all of our competitors sort of keep it as 2 separate files, which you've got to keep track of and manipulate accordingly. So we handle them as complex numbers.
Great. So Gabriel, I've got a question for you. So you have a background in radar, polarimetric radar, but you also have a very rich background in applications. What do you think this means from an applications point of view? Like, how is that going to be different for people who are doing a lot of these different applications, being able to work this way?
But of course, if you can treat Sentinel-1 tops data as any other SAR image, that means that there is way less manipulation to do. So you can focus mainly on the analysis that you have to do. You will spend more time on doing your application, developing, let's say, scripts to extract the information you need from the imagery. Because like you say, all the heavy lifting and the bursting, the ramping, everything is done really under the cover for you. So you can, like I've said before, you can extract the area of interest. And so you will spend way less time to doing the pre-processing and processing of the data. Typically.
Great. Yeah, do you want to add something, Guy? Or?
I want to say that, yeah, we do all this so you guys can focus on the fun part with the analysis.
Yeah, for sure. So I'm just going to throw a quick poll up on the screen because it's good discussion. I'm going to go to the applications next. I want you guys to stick around. So I'm going to throw poll number 2, which is what challenges are you currently encountering with SAR image analysis? So maybe working with individual swaths, as we've described, you find that cumbersome. Maybe you're finding that processing software is slow and difficult. Maybe you don't have a way to do automation, and that's something that you're hoping to achieve. Maybe you find the integration of the different steps to be cumbersome as well. Like you have to ingest separately, you have to do the InSAR separately, you have to geocode separately. You know, these are some possible options that you find frustrating. Certainly, we've processed a lot of data as we've developed the software and have been testing it. And so these are some of the things that we find people have been sort of bumping into. And if you have another issue that you've been encountering, by all means, let us know in the questions box. And so Jason's just flipping the laptop over so the gentleman can see the answers. So thanks for giving this feedback. It's great to be able to get this direct feedback here with our staff. Thanks for giving you this input, or giving us this input. I'm going to close it down in just a few seconds here. So I'm going to close it in 3, 2, 1. I'm going to share out the results. So there was no right answer. You could select more than one. So poor integration of steps, processing software is slow and difficult. You know, you can see the results there. So that's really useful. Thanks for giving us that info. What I'm going to do now is I'm going to reverse the order, and I'm going to talk about a few applications. So the first thing I'm going to do is stick around, don't go anywhere. So I'm going to talk about Ridgecrest, which is an earthquake that occurred last summer. So as this tool was being developed over the summer, I was pretty keen to start using it. As soon as I saw that there had been an earthquake, and I heard from Guy and Gabrielle and John that the software was kind of getting there in terms of being ready, and I thought we would use it as a real test case to put our software through its paces. So there was an earthquake that occurred over Ridgecrest. Luckily, it's in mostly not a very populated area, so nobody was really harmed or anything like that. There was damage to property, but basically there was a magnitude 6.4 earthquake on July 4th, and then there was a aftershock on July 5th of 7.1, which was bigger than the original earthquake. So what we did is we downloaded the Sentinel-1 TOPS data, which was actually available very, very quickly. I remember coming in to work the next day after this earthquake, and I saw that there was an image that had been collected on July 4th, just before the earthquake. So I immediately downloaded that, and then I patiently waited 6 days until the next image was collected, which was on July 10th, and I was able to download that image pretty soon thereafter. So I did that using Sci-Hub, ingested based on an area of interest just over that small AOI, which we're capable of doing, and then process it through the standard InSAR workflow. So basically, this is just a few screenshots showing you the actual images. This is the search parameters. The location is just north of Los Angeles here. And these are all the images that are available. And I'll get to this in a minute, but you'll see that the collection cadence or frequency is quite high every 6 days or every 12 days, depending if you're mixing the Sentinel-1A and 1B. And so what you see is a backscatter image in the back, and then one of the subsets that's been ingested. So in this case, I chose just to work on the central part of the image, and you can actually see that it overlaps 2 swaths, and it definitely overlaps multiple bursts. But that's not an issue. Just point to a piece of the image for processing, ingest that piece for both the reference and the dependent file, and then start processing the data. So this is just showing you the 2 images that were downloaded. These are just the backscatter images. Of course, we don't see the fringe patterns related to the earthquake yet. These are just the backscatter images. But after running the script and getting the results, we basically were able to get this very, very signature fringe pattern. And I can get probably John to explain it best. I can take a quick stab at it, and John can explain in more detail, but essentially what we're seeing in the middle, what we see underneath is the coherence layer. So that shows us how strong, or how areas that have not changed are white, and the areas that have changed are dark. So you can see some crop circles on the left. So there's been moisture or irrigation or something like that has happened that's disturbed the backscatter. So you don't have high coherence there. And the main thing that you see is along the fault line. So this big dark area in the middle is basically a loss of coherence. And then what you see on top of that are the fringes. So basically what it's showing is From one cycle to the next, it represents half of a wavelength of movement on the ground. So it's a 5.6 centimeter wavelength, so about 2.3 centimeters of ground movement over a certain space on the ground. So you can see as the fringes are farther apart, it represents less movement on the ground over that space, and as they're closer together, it represents more movement on the ground. And you can definitely see that as you get closer to the epicenter, you basically see quite a lot of close fringes together representing the movement of the ground, basically. John, I'm not sure if you want to add something to that, or?
Well, the interesting thing too is to note that the order of the fringes goes in opposite directions, so you can actually tell which part of the plate is moving towards the radar and which part of the plate is moving away from the radar, and that's
The colors. You mean the order of the colors, right?
Yeah.
Okay.
So you'll notice that on the left-hand side, the order of the colors is reversed from the right-hand side. And of course, as you pointed out already, that where the low coherence is where things have been disturbed so much that we can no longer measure the fringes, and that's where the earthquake was most severe. And you can actually see the sort of, you know, where the plates sort of slide against each other.
And John, we see a lot of small pockets of patterns. Like, you know, we see these patterns. I don't know if you can see my mouse or not, but there's a pattern over here, and there's another pattern over here, and basically, this is July 4th to July 10th. There's about a 6-day window in between. What are we seeing? Are we seeing like one big ground movement from one date, or multiple movements, or?
Well, this would represent the difference between whatever the reference image is and the dependent image. So I don't know exactly which pair you took, but
4 to 10, July 4 to 10.
Okay, so was there one earthquake between them or two?
More than, well, there was the main earthquake, the aftershock, and then more trembles.
And you would think I knew that because I was in California that day. Yeah, so I mean, yeah, this would be the sum of all of those changes.
Right. Great. Okay. So just interestingly as well, what we did when we did this analysis, we posted some messages on social media, and we saw some other scientists and researchers around the world doing similar work with other types of data. And it was actually kind of interesting to see some of the results from ALOS PALSAR 2, which is different wavelengths, a 23 centimeter wavelength. So half wavelength is roughly 13 centimeters. So you can see that the fringe pattern is similar, but the spacing is different because of the antenna differences, basically from, you know, L band to C band. The wavelength. Sorry, yeah.
So it's 4.5 fringes to 1.
Right. So they're quite further apart in the example, but the displacement pattern, the you know, where things moved is very, very similar. So anyway.
So in the first one, you multiply by half of 23.
Mike.
Yeah, so the PALSAR images represent about 11.5 centimeters per fringe, and the other ones are about 2.7. So
great.
About a 5 to 1 ratio.
Okay. Okay, so I'm just going to quickly show some of those results. So here I actually have the project. So I'm just going to zoom in here, or zoom out to the extent. So you can see that I'm just working with a piece of the image. So that's the piece that had the, you know, I centered my analysis on the epicenter. So here's one of the images. So this is the actual backscatter image from one of the dates. And then we have the coherence layer, and then we have the actual interferogram. In this case, it's the interferogram that's had the topographic phase removed. So we supply an external DM to remove the topographic phase. And then we also perform the INS adjust algorithm to remove any residual atmospheric effects. And then what we have is the residual phase patterns, which are represented here by the fringes. Couple of interesting things. So what you can do in our software is you can basically, if I load up an interferogram here, so this is an interferogram, and you can see that I can actually right click and go view, and we have this special capability to view as amplitude and phase. So what this does is it loads the data for you with the coherence layer underneath and the interferogram over top of it. So it's kind of a nice simple way to look at the data. You can see that when I did that, it just loaded it kind of in a very nice way. You know, we try to make it easy for you to perform analysis and to visualize the data. Some other things too, if we look at the actual backscatter image, I'm not sure if this is going to work or not. So we have the ability to represent the data as intensity or amplitude, phase, decibel, kind of on the fly. You know, we store the data as a complex data set and just represent the data for you, the user, the way that you want to see it interactively. You don't have to generate multiple images in all different matrix format and so on. So anyway, this data set is freely available and we have scripts available. So if you want to replicate this and you want to try it out, you know, we'll be providing you with a PowerPoint presentation. You can go download the same images we work with and achieve kind of the same results. So I'm going to move now to the next example, which is interferometric processing for deformation monitoring. And we're staying in California here. We like California. It's good for InSAR because it's nice and dry. You don't have too many disturbances relating to coherence. So this is basically a very well-known on-land oil reservoir just to the west of Bakersfield in California. And there's a series of oil deposits in this area. And you can see these sort of gray areas here on top are showing you where all the different reservoirs are. And I've actually visited this personally for work. And I can tell you that these oil drilling rigs are really, really close to each other. Like you could, you know, you could throw a soccer ball over or something over. Like they're generally around 20 to 30 meters apart. So they're really close together. And you can see that in between, it's very arid. And what's happening in this area is, I've actually got a little video that explains the process. So here on the left, you can see kind of an animation of the steam injection or water injection process. So in order to produce the oil, what typically is done is a pipe, a well is dug into the ground. And so the initial oil in this part of the world will be able to be pumped out, but then to sort of get everything out of the reservoir, they use different techniques. So in this case, they use steam injection or water injection, hot water injection. And you can see the sort of the factories that are generating power and heating up the water, and then that water gets pumped into the ground. You can see on the right-hand side and on the left-hand side, these pipes going in, they're injecting hot water or steam. And that's kind of stimulating the oil, and it allows it to then be pumped out in the middle by the well, the oil well in the middle. So of course, this is very expensive equipment. These particular wells here are on the order of hundreds of thousands of dollars, if not millions. And what oil companies are really concerned about is movement of the subsurface up or down, so subsidence or deformation up or down, because if you get too much subsurface material pushing down on pipes, basically it can cause the pipes to shear, and then that would render the well kind of useless. So very expensive to replace. And obviously they're trying to avoid that. So there's a lot of different techniques that have been used over the years to do ground surveying and measuring with prisms and a lot of different techniques. But kind of starting in the early 1990s with the advent of ERS-1, which was more reliable as a sensor collecting data than RadarSat-1. And now with Sentinel-1 and commercial sensors like TerraSAR and RadarSat-2, this is actually an operational way to monitor and inform decisions about how much oil to extract and how much steam to inject to manage that very delicate balance to ensure that the equipment is not damaged. So what you see in the middle here, I found this really interesting article. If you want to read up on it, there's a poster paper I found from an energy company that traces the 100-year history of the Belridge oil field. So it's quite interesting. There's a lot of good information about the production processes and some of the different technology that's been used. But what I found on this gentleman's poster is actually a screenshot of a deformation map from Belridge showing the, I think it's a cumulative displacement over a particular time period. which is the map in the middle. And I've actually got an example of that that Gabrielle developed using Sentinel-1 data. So basically what Gabrielle did is downloaded 22 images, all in ascending pass. The time span is basically November 2018 until September 2019, so it's about a 10-month period. Gabrielle ingested based on an area of interest, so as not to process the entire image. Processed it through our standard InSAR workflow, unwrapped all the interferograms, and then was able to stack them. We have an algorithm which I didn't list in that big chart there. It's called INS stack. And what it can do is it can actually take all of the interferograms and allow you to measure either the cumulative displacement or the velocity of the displacement over time. So I think it was velocity that you did in this case. Just a quick note about the revisit. So I put this together to give you a sense over a typical month. So this is November 1st and November 30th over Belridge. I actually went in Sci-Hub and did a quick query, and you can see when the acquisitions are occurring. So ascending and descending are occurring basically within a 12-hour period of each other, which makes sense. But then between Sentinel-1A and Sentinel-1B, you can see that there's a gap of about 6 days. And then if you want to wait for the same sensor to collect the same geometry, you have to wait 12 days for that. So in the case of this data set, we did the Sentinel 1A or 1B, I forget which one, 1A. So we did Sentinel-1A ascending, and so it was every 12 days. However, you could do Sentinel-1A ascending, Sentinel-1B ascending, which is actually what I did for the Ridgecrest earthquake. So in that case, you have a 6-day separation. So what that means is you get about 10 measurements per month. There's also a way to combine ascending and descending. You can process them separately, then you have to sort of consolidate that information into one stack. Anyway, there's still some work to be done there, I think, on our side, but it is possible to do that. Here's kind of an animation of Gabrielle's results. So basically what we see is the sort of the background image is a Landsat image, just kind of showing you the location. And what we did is we took the cumulative, the velocity over the period of time. So, well, maybe you can explain it, Gabriel.
But instead of accumulating all the changes, we are just basically measuring how fast the ground is subsiding, uprising or subsiding between every measurement. So what we want to know in that case, how do the surface oscillate? Right. It's not how much centimeters did it move across a year. It's really the rate of change.
Rate of change. Yeah. Okay. And obviously, if that rate of change starts to accelerate, then maybe that's a problem. And if it starts to, do the other thing as well. So if it's accelerating up, that means potentially the steam pipes are in danger. Is that right? Or have I got that right? Or
if it's moving too far.
John?
No, I was just going to say, the key thing is with velocity, you want everything to be moving up and down at the same rate. Otherwise, you put a lot of strain on the pipes, of course.
Right.
So if one part is going up much faster than another part, then there's a lot of strain on the pipes.
So the spatial pattern and the rate of change are kind of the two key things that people use this technology for.
So if it all moves up together, that's better than if part of it's moving up and part of it's moving in the opposite direction, of course.
Right. And we don't have the detailed information on the wellheads, their location, but oil companies obviously have that information, and they overlay this type of information on top of it to make decisions, right?
And I just want to point out too that it took around a day to process all those 22 images,
right,
including the unwrapping.
Right.
And it was a fairly, not a small region, not a big one, but it was like 15,000 pixels per 5,000 columns. So it was a good data set.
Yeah, and I mean, I've seen the scripts you've written. You've got everything from ingesting to generating the interferograms. Like all of those steps are really well put together in the Python scripts, and we'll be making those available for sure. So I'm going to go to maybe you can keep talking about the results, Gabrielle. I'm going to pull them up here kind of live as we're going. So you can probably see my screen, but basically here I'm just showing the Landsat 8 image, and this is actually the oil field map. So I think we found a topographic map that shows where the reservoirs are located. We generated some masks, so just to kind of orient you as to where we are. So, you know, Los Angeles is down here and Bakersfield is over here, I guess. So then the next step was basically to ingest the imagery. So this is the piece of the imagery that you work with, is that right?
Yeah, this is around the central part of the image.
Central part. And the Sentinel-1 data has 2 channels, pretty much always, right?
Yeah.
And is it always VV, VH,
Yeah,
or?
basic collection mode is, for the IW mode is VV and VH. So in that case, I've only processed the VV.
Okay.
The channel.
Right. We re-ingested the data with both channels, which is why you're seeing color right now, I think. Yeah, and so then we move to the flat Earth deformation. So maybe just walk us through that one. We've just got a few kind of results here up on the screen. So this is the fringes still. This is not unwrapped, right?
No, this is not unwrapped yet.
Yeah. So this one is April 4th to April 16th, and then another one is from, they're just sample interferograms that we put into this gallery. But we have, basically we have all of these deformation products.
Yeah, because one thing that is important when you're doing InSAR processing is, well, we talk about all of those Python scripts, but we do inspect the result in a couple of steps, because the way the Python script are built or the way we're doing InSAR processing is often after the raw interferogram, we go and we look about both the coherences and the fringe pattern, because if after INS-RAW, if after the raw interferogram generation, you don't see any, how can I say, any special patterns or anything good, that means that it's useless to go further into the processing chain. So
Right. So when you look at these interferograms, what are you seeing that tells you we're going to have a good result?
it's part based on feeling also, but what you can see here is you can see really good patterns. So also, I'm not sure which interferogram you're showing here.
This one is April 4th to April 16th.
But is it the raw interferogram? Or?
It's defo raw.
Yeah. So now, yeah, the deformation have been removed.
Right.
Not the deformation, sorry, but the topographic phase have been removed. So what we are left is only the difference in distance between the 2 satellites. This is the raw interferogram. So
you can see, I don't know if you can see my mouse or not, but you can definitely see a little bit of a pattern here. So the oil field is right along here.
Yeah.
And you can even see in the fringes that there's a bit of a pattern there and here, I guess, and in other areas as well. So that's what you look for. You look for things that kind of make sense visually, right?
Yeah.
Right. Okay, so then we move on to the deformation maps. So that was basically the animation I was showing earlier, but these are kind of like the raw products. So these have all been unwrapped, and now they're in what units?
This is in meter per year.
Right.
But this image is a color composite.
Yeah, I understand, sorry. But the colors represent the movement, so I'm just going to show this here. Yeah, so sorry, maybe you can explain. This is the rate of change per year with your legend, right?
Yeah, this is really in meter per year.
Right, okay, so then I'm gonna move over here and I'll just turn this off, turn that off, and I'm just gonna leave the masks on, I guess. So we have this tool, so I'm gonna pick this one and do the temporal charting. And I'm going to change my, so basically what I'm doing now is what Gabriel did is he created a stack of data that has all of the unwrapped interferograms. And what I'm doing now is I'm basically plotting the changes on the ground. So I'm going to place my cursor. Oops, I have to sort of change my windows around here.
Too many windows.
Yeah. Okay, have I got the right layer
Go
there?
from -50 to 50.
Yeah, did that. Oh, I think it's because I resized my window. Let me do that again. Layer, temporal analysis, there we go. Okay, yeah, so basically we have the full 10-month period here, like from 0 to 0.9, that represents the 10 months. And then as I move my cursor over certain locations, we see this oscillation, right?
Yeah. The velocities are changing
across
time.
Great. So there's this tool available for looking at those changes. Obviously you can generate these results. I'm gonna keep moving along here, just losing track of time here. So I just want to highlight some resources. So we have further resources. Customer support team is here to help you. We got our Python scripts. We're going to talk about a few more things. You want to talk again? Got some.
I just read a question that.
Okay. We'll get to the questions at the end, don't worry.
Okay, perfect.
We're gonna get there. We've got some tutorials on our support site. We've got a Udemy course. Actually, John and Gabriel both gave a course here in Ottawa in February of this year, and we recorded everything, and we have one of the days available through Udemy. It's also, all 5 days are available on YouTube. It's kind of long to watch, but we do quite a bit of SAR training around the world, and we make those available. And we also have Jason and other people in our company who kind of wear a different hat. They're more like technical solution specialists, and what they do is they can work with you to see if Geomatica is a fit and work with your data and explain the workflow and sort of get you going faster. So I'm going to just ask my last question, and then we're going to do some Q&A. So just to kind of ask you the question about the thing I just mentioned, which is if you have a project in mind and you don't want to I don't want to say waste your time, but if you want to spend otherwise valuable time learning our interface and you just want to see whether the results that you're getting with your data in our software are suitable or not, you can use people like Jason to run data. We have a benchmarking program. Basically, you can send us data, we'll work with it, we'll process it, and we'll put a bit of a summary presentation together. We'll send it to you, and then we can organize a meeting and show you the results. So I want to make sure that that is understood. We have that option available. More than happy to do that. So I'm going to close that down. Thank you for those of you who answered that one. And I'm going to go to questions, I guess. We're getting close to the hour. It's kind of busy here. I don't know if we have time to talk about the future before we go to the questions. I'd like to talk about the future. So, John, I'm going to throw some slides up on the screen. I don't want you to explain them all in detail, but maybe what I can ask you is, where do you see, just in general, where do you see SAR kind of technology evolving? Like, what do you think's next?
Well, I think the first thing is we're going to have to learn what to do with all the data that's coming down the pipes. I mean, there's a whole bunch of new sensors that are coming out. The Europeans are launching a biomass SAR sensor, which is P-band, so that'll be new. And US is launching the InSAR satellite next year, which is L and S band. So you'll be able to get X, L, C, S, P band in all 4 polarizations, and you can do all the synthesized things that you want to do. So there's a massive amount of information coming down the pipes. And so the ability to acquire data, at very short intervals. So there's a lot of commercial companies becoming available. You'll be able to collect data, every couple of hours, essentially.
I understand you've seen some of the ISI data, some of the latest ISI data.
So it's all fantastic stuff. So it's just massive amount of data coming down the pipes, bistatic, TOPS mode, spotlight mode. So you get all the different permutations, you got a range of resolutions. So there's just like practically any kind of data you're going to want. And orbital information is very precise now. So the ability to geocode and calibrate and take all that information and put it into one big ball is going to be available. So guys like navigation guys like this guy.
No, but I mean the challenge will be to integrate all those information into the synergy between all those sensors to extract valuable information.
Right. So I've got a few slides that kind of describe kind of some of the technology that we're developing, but I've summarized it here. I'll just cycle through them a little bit. Maybe you guys can explain a little bit kind of where we're going next. So we've got, well, I guess a Sentinel-1 interferometric wide data set, and then we have the ability to synthesize. Maybe you can describe a little bit here what this is and why it's beneficial. The hot
Certainly.
mic.
Yeah, so basically using a DEM, external DEM, and the state vectors and other information of the scene that you want to synthesize, you can basically synthesize what the backscatter would be according to the elevation model provided. And that's basically that PS synth tagged image there.
So that's the SRTM DEM, and then we have the...
Yeah, so this is reprojecting that DEM to the geometry of the SAR scene.
Okay.
As was Topsy said, right?
Yep, Sentinel-1 IW, yeah.
Yeah, so reprojected to slant range. So all the usual foreshortening and layover and shadow areas are all being calculated, and pixels are being reprojected according to where they show up in the slant range geometry.
Right. So there's an image coming up here which you can explain in a bit more detail. But here we have a ortho-rectified Landsat image, and you can see the mountains and so on. And then I guess what we did here is we took the geometry of the radar image and then projected the Landsat image into that projection. Is that right?
Yes.
Is that what we're seeing? I'll just go back and forth here.
Yeah, because when we talk about the integration of different sensor and different kind of information, the first slide you shown was the ability, like Guylain said, with the state vectors and with the DEM to synthesize the image. So why are we doing that is to be able to know where the layover and foreshortening are, so we can create masks. So that's help us with the analysis. But the most important thing is to do a true segmented calibration, is to remove the effect of the topography. So if you're about to do a time series analysis, or if you want to, let's say, integrate ascending or descending image, you want to remove this topographic effect. Even if this topography give a good look to SAR imagery, in my opinion, sometimes, yeah, you have, from a statistical point of view, you have to remove it.
Yeah, we have an image here where we've removed the topographic effects, and to the eye, it's kind of unusual. We're not used to seeing imagery this way because we take our cues, our interpretation cues from the shadows, and
And when we talk about also the integration, the second part, the calibration is really the first part. But since now we know pretty well the geometry of acquisition, so that's mean that we are able to take any other piece of ancillary information that is already ortho-rectified. This can be a Landsat image, this can be a DEM, could be Sentinel-2 image, or we can take any ground truth points and reproject it onto the slant range geometry of the SAR image, if it need to be. Because there's always a theory that says that closer you are from the measurement, from the signal, less distortion you will introduce, so better will be your analysis. So the possibility to pass easily from the radar geometry or to the ortho-rectified geometry and back and forth really gives a lot of flexibility to people's workflows.
So one of the big topics here at PCI is analysis-ready data. How does this all play into analysis-ready data? Like, where do you see that going with radar, and why is this important for ARD?
But like John said, there is so much information now that's coming down the pipe, to reuse this expression, that we need tools to gather data together in a format that is ready for the analysis. So you don't want to spend too much time by pre-processing your data, by processing them, and you don't also want to introduce errors, because some people are not, let's say, SAR scientists, but they want to use the benefits of SAR data for like moisture estimation or for like biomass with the P-band mission that will come next year. But sometimes it's knowledge or tools they don't know really. So with the analysis ready data, with all the foundation that we're building here at PCI Geomatics, all those tools that can get our data together, the ultimate goal is, yes, to bring all those data into analysis ready data so people can put their effort into the analysis and their workflows.
Okay, so we're going to move to questions now. We got quite a few questions coming in. Do you see something you want to answer?
Yeah, I'll answer this question.
Okay, well, let's read it out first, or can you summarize it? Or so According to poll number 2, 2 questions. Does Geomatica have algorithms to detect oil slicks in offshore areas? Does Geomatica have tools for polarimetric decomposition with quad pole images? I have some quad pole Radiosat 2 images, and I like to test parameters like entropy, 2Z, correlation coefficients to characterize oil slicks detected with Sentinel-1 images.
Yeah, so I'll answer the second question. We have a full SAR polarimetry workstation that includes entropy, alpha, beta parameters, 2Z decompositions, polarimetric discriminators, and a whole other list of things that I can't just list off the top of my head.
Sure.
And I absolutely, so you go for that and see what you can pull out.
Yeah, we didn't really focus on that today. We focused on TOPS, which is primarily used for, well, we see it used a lot for InSAR, but it's used a lot for lots of other applications. Maybe a few words about oil slicks, since the question was relating to oil slicks. Best practices, VV, kind of tough, right? Sentinel-1, VV?
Yeah, with VV, we'll have too much of a wind effect. So usually we'll go either with HV or HH.
Right.
So you're not really sensitive, but you will be less sensitive to the Bragg skittering that occurs over ocean surface.
Yeah, I mean, what I've seen over the years is HH or HV cross pole is kind of the perfect way to do that kind of application. But in terms of, putting together those kinds of workflows, our software has a lot of algorithms that can be, built and
I think to answer the question completely is
sure.
We don't necessarily have like the tools that you have and you input the image and do oil slick detection. But we do have lots of tools that allows you to threshold, to do an object-based segmentation based on the intensity or other polarimetric parameters. It allows you to detect those slicks. But there is different ways of doing it.
Okay. So we have a question, it's kind of a good one about the application, I guess. So what is the recommended data gap between the images, especially in active and slowly deforming areas? I guess the question relates to the separation in time of the collections.
Well, there's a couple of things to consider. I mean, clearly if it's slowly deforming, then you don't need to get data really very often. I mean, the critical thing is you have to acquire data at least at a rate that whatever is moving hasn't moved more than half a wavelength. So obviously if something is moving quicker, then you probably want to go to a longer wavelength. If something is moving relatively slowly, then shorter wavelengths are probably the way to go. So yeah, the point is, first of all, again, it depends where you get your data from and how much you can afford and that sort of thing. But mostly, yeah, if it's moving very slowly, then you can get it often enough to capture the cycle of whatever it is you're trying to measure, because sometimes it's linear, sometimes it's cyclic, and so you have to get measurement points at the times where things are peaking and going down, kind of thing.
Okay. There's a couple of questions that are kind of related. I'm going to try to answer them, but I might flip it back to you a little bit. So one question is about the license kind of not working with the trial version, and I think it's probably related to snafu. So I'm going to go there. So someone is asking why it's not working, so our trial license basically has everything working as far as I understand. However, if you're going to try to unwrap the interferograms, you do need to install a third-party software package, which we can't distribute as part of our build. So we make it available through a Git repository. So you have to go grab that file, put it in a certain folder. So if you ran into a problem with INS Unwrap, that's probably why. But just along that same vein, if I can ask you three guys, a related question, which is about the unwrapping. So basically, previous version was snafu. Is this version still snafu? What improvements have been made? What's kind of the plans or the status right now as it relates to phase unwrapping?
No, snafu is still the unwrapper we use. And like you say, we need to install, which is not, it's just easy because Guylaine did a great job that there is an executable you can directly download and place into a directory inside the Geomatica. I don't know if you can show it on
Yeah,
screen.
I can show it for sure.
But there is nothing to install. It's just grabbing a file on the internet and to place it in the third party.
So PCI Geomatics, Geomatica BAMF, third party, and then there's this folder that is part of the install called snafu. and usually it says install snafu. So on my machine, I haven't installed it. So if I open that text file, basically it points me to this website, which is the Git repository, where we basically packaged it so it would be easy for people to, well, it was compiled, I guess, right? So they could just drag and drop an exe file into this folder?
It's a zip file.
Zip file.
But yeah, you just extract it in there and then you're good to go.
Yeah.
But we choose, for the moment, we stick to snafu because it's still a strong unwrapper.
Yeah.
I know that people sometimes can have some criticism over snafu for being a bit slow, but we have really lots of tools that we can use to make it unwrap faster. So you can apply, let's say, a Goldstein filter to improve the fringes. You can also do a multi-looking on your interferogram, and that speed up a lot.
Right.
After applying a multi-looking, or you can even.
So that's something you could do now.
Yeah.
You just have to kind of do it yourself, right? It's not kind of built into the unwrapping capability at the moment, but
it's part of the pre-processing before going to snafu. So
right.
we have a script for multi-looking.
Right.
So let's say you reduce the number of line and column by a factor of 2. So
yeah.
you will increase a lot the processing speed. And at the end, we don't often need, when you're doing deformation analysis, or even if you're trying to use extract a DM, we don't need a full resolution most of the time.
Right.
And you can also launch snafu like 2 or 3 times,
okay.
or 2 or 3 times, or processing in parallel too. It's
sure.
also possible. You can do it either manually, or you can do it through a script, launch snafu for our first interferogram, and launch another one, so you don't have for the first one to finish.
Okay. We've got a question about, does PCI support the PS algorithm? So I think what they mean is the persistent scatterer.
Not in the defined way that it is right now. We do allow you to identify stable points, and then we use them, which is basically what persistent scattering does. Persistent scattering wants you to process all the permutations of all the interferograms, identify the highly coherent points, take the trend, and then use that to correct for atmospheric effects. We basically have put it on the user to identify the areas that they figure are stable, because we anticipate that in an operational setting, most people will know the areas that are stable anyway. So we just cut that part out, but we will get around to it.
But from just a technical point of view, if I can add details, when I want to do like that kind of analysis, what I'm using, because when you're generating a stack of data, we're generating coherence layer. So I often do a kind of simplistic analysis and then look across my stack, all the points that have remained coherent across the entire stack with high coherence.
So you can use that as a way to mask areas where the results are not really.
If the points have remained coherent, highly coherent across the stack, they are like persistent scatterers.
And there's an algorithm I didn't talk about, but there's a new one called dilate bit. Can you guys describe that and how it would be used in that context?
Well, it's exactly like Gabrielle pointed out. You can generate a stack of data sets, and you can identify all the areas that exceed a certain coherence, and then you can set a bit mask for those, and then you can filter around the bit mask, and you can set a buffer around these things. And
so low coherence areas would be eliminated from the unwrapping process.
That's the converse of that. That's the way I generally use it. Is I generally look for areas that are below a certain threshold, and then just mask them out automatically, and then put a buffer around it. And you can filter based on the buffers and things like that. And Guy's done a really good job, sort of erosion and dilation effects. So it's a very easy program to run. You can run like multiple layers of erosion and dilation in whatever order you want to do it in. So
great.
It's really a very, very powerful tool, and I think this is the first time it's been released. I think this. I
think so.
Yeah.
And this release,
I really like that tool too.
7 minutes past the hour. I don't like to keep people too long, so I'm going to cut it off there. I want to thank you guys for being part of this today. I think it's really great that we're able to include you. I hope you found value. All of those of you who attended, thank you so much for being here today. I'm just